Okay, let's say I want to describe the vector equation of a plane. In other words, I want the vector that takes me from the origin to any point on this plane. How could I do that? Well, firstly, I need to get onto the plane, right? So I need a vector that takes me onto the plane, and I'll typically call that vector the vector A, right? So A takes me onto the plane. And then once I'm on the plane, I need to travel in a direction parallel to the plane, right? So I'm going to call that vector there the vector B. Now, if I just have one vector B, then I'm not able to get to every single point on the plane, right? I can only travel in the direction of B like that, which means I would have a straight line, not a plane. Okay, so if I want to get anywhere on a two-dimensional surface, I'm going to need two vectors. So I need another vector here, which I'm going to call C, and C must also be parallel to the plane, but it must not be parallel to B. In other words, if C was in the same direction as B, then again, all I'm going to get is a direction of a straight line, to travel in a straight line. I can't get to every single point here on the plane. Now, what does that mean? It means that R is equal to A, I get onto the plane, plus lambda lots of B, plus mu lots of C. Okay? All right then. But we can also describe a plane in Cartesian coordinates using x, y, and z, and that involves understanding the normal. Now, what is the normal? The normal is the vector which is perpendicular to the plane. So I'm going to try to draw it on here, right? So the normal, which we'll call n, is the vector which is perpendicular to the surface of the plane. Now, that means that it is going to be perpendicular to B and also perpendicular to C. So how could we find that vector? Well, the normal vector will be equal to B cross C. Why is that? Because the cross product gives us the vector that is perpendicular to the two input vectors, right? So if I do B cross C, then what I get as a result is a vector which is perpendicular to both. Now, if that is the case, we also know that B dot n will be equal to 0 and C dot n is equal to 0. Why is that? Well, because the scalar product or the dot product of two perpendicular vectors is always 0. Okay? Now, that is remarkably useful because if we were to take this entire vector equation here and scalar product it with n, something interesting is going to happen. So if we get r dot n is equal to a plus lambda b plus mu c dot n, and the dot product is distributive, right? So I can kind of treat it like I'm expanding the bracket. So I get a dot n plus lambda b dot n plus mu c dot n. Then what's going to happen is, well, we know that those two guys are 0. Okay, so now what I'm left with is r dot n is equal to a dot n. Now, r, how could I write it? I can just say that r is the general vector, which is x in the I direction, y in the j direction, and z in the k direction. So I can take this guy here and say, all right, I have got the vector x, y, z, scalar producted with the normal vector. Now, the normal vector I'll call n subscript x, n, y, n, z, is equal to a dot n. Now, a dot n is just going to give me a scalar, right? So I'll call that scalar there d. And if I was to expand this, I get nx times by x plus ny times by y plus nz times by z is equal to d. And that thing there is what we call the Cartesian equation of the plane, because it's given in the form of x, y, z. But what is so interesting about that is it tells you that the coefficient of x, y, and z tells you the direction of the normal. So, for example, if I was to have the plane 3x plus 2y minus z is equal to 5, I would know that the normal to that plane is in the direction 3, 2, negative 1, right? That's a very, very important thing for you to know. However, this guy here, D, right, also tells me something quite significant, right? So in order to understand that, we need to go back to our diagram. Let us say now that I was to draw the normal, not at this point here, right? So I'll get rid of that, but defined through the origin. So I'm going to draw my normal vector going from the origin like that. Ooh, let's do that a bit better. Like that. Oh, blast. One more time. There we go. Okay. Now, that's my normal vector. Now, if I was to do that, what I could choose to do is to create a right angle triangle that's like this. Okay, right angle triangle like that. Okay, and that's what I'm going to do. So let me try to do that. I'll do that in highlighter, I think. So I want to create a right angle triangle, which is there to there, there to there, and there to there. Okay, so we got a right angle here. Now, why are we interested in that right angle? Well, because this distance from here to here will be the shortest distance from the origin to the plane, right? So that distance there is the shortest distance from the origin to plane because it is along the line that runs perpendicular to the plane, right? So it's impossible for me to get any closer. So I'm gonna call that distance. What should I call it? I don't know. I'll call it capital D. Okay, call that distance there capital D. Now, what's this distance here? That distance is the magnitude of A, isn't it? So I can call that the magnitude of A. And this angle here, which I'll call theta, is the angle between the vector A and the normal vector. Now, if I think about that very carefully, if I just go across to the left, using trigonometry, I can say that D is going to be equal to the magnitude of A times by the cosine of theta, right? That's just trig. Cosine is the adjacent over the hypotenuse. And so therefore, this distance here, the adjacent side, is equal to the hypotenuse, which is the magnitude of A times by the cosine of the angle theta. Well, I can convert this into a vector equation. The way I'm going to do that is with a sneaky little trick that you need to learn because you're going to be using it all the time. I am going to introduce the unit normal vector, right? So I've got the magnitude of A, I've got the cosine of theta, and now in between this, I'm going to introduce this thing here, the magnitude of the unit normal, right? So we've got the normal vector here, but this little hat means we've got the vector of size 1, okay? The vector of size 1. And so therefore, if it's a vector of size 1, the magnitude of that will just be 1. Right, so I've still got A cos theta times by 1, right? So nothing has actually changed in terms of the value. I've just kind of introduced that there. Now, why have I done that? The reason I've done that is because I know that the scalar product rule is if I've got vector P dotted with vector Q, that's equal to the magnitude of P times by the magnitude of Q times by the cosine of the angle between those two vectors. And so therefore, if I look at that, I can say, wait a second, this is the same thing as A dotted with n hat, right? Because here I've got magnitude of A, magnitude of n hat, the cosine the angle between them. So this is just A dot n hat, which is the same thing as A dotted with n divided through by the magnitude of n, right? Because the way to get the unit vector is I take the vector and I divide by its magnitude. So if I was to go over here, right? And we've got r dot n is equal to a dot n, right? This form here. If I was to change that ever so slightly, right? Instead of dotting with n, I dotted with n hat, then r dot n hat would equal to a dot n hat. And what is a dot n hat? That thing is the shortest distance between the origin and the plane, okay? Or another way of doing that is to say I do my r dot n is equal to a dot n, but then I divide both sides through by the magnitude of n, right? The magnitude of n, okay? So what does that mean? Again, let's just do a quick example. If I've got 4x minus 3y plus z is equal to 10, well then what I know is that the magnitude of that not the magnitude, sorry, the normal to this plane is going to be 4 negative 3, 1, right? So that's the coefficients of x, y, and z. I can then find out the magnitude of n, which is going to be the square root of 4 squared plus negative 3 squared plus 1 squared, which is going to be equal to root 26. And so therefore I can say, wait a second, the shortest distance from the origin to the plane is going to be this guy here, the 10, divided by root 26. So the shortest distance is equal to 10 over root 26. Okay, and what I'm hoping really is not that you memorize these formulas, right, but that you understand the step that I did here, right? This is the key thing, because if you can understand this, you'll be able to understand all of FP1 vector problems much more easily. We are moving from a trigonometric problem, right? That's that thing at the top, to a vector problem. And essentially, that's what we're doing in most of these questions. We're moving from trigonometry to vectors. And the way we're doing it is by using either this scalar product rule or later on the cross product. Okay, so if you can understand how to manipulate that, you're going to be in a much stronger place. All right, let's get on to a question, I think. Okay, so let's try out a question. This is from May, June 2024. So we've got 3 points here. The points A, B, and C have got these position vectors relative to an origin O. We want to find the equation of the plane ABC, giving our answer in the form here, which is the Cartesian equation form. Okay, well, the first thing we're going to do is we're going to write out all those points in column vector notation, right? Basically, you want to use column vectors by default because it makes everything a lot easier. So OA is 2, 2, 4. OB is equal to 2, 4, negative 1. And O to C is equal to negative 3, negative 3, 4. Okay, now let's try to think what's going on here. We've got a plane, so I'll try to draw that out roughly. So we've got a plane like that, like that, like that, like that. Okay, and here's our origin point. So say that is O. And we've got these 3 points here, right? So A and B, and let's say that's C there. Okay, and I said earlier that in order to describe a plane, we need to do a couple of things. Now, the first thing is we need to actually get onto the plane. So we could either go to A or B or C. It doesn't matter. We just got to choose one point to take us from the origin to the plane. Once we've done that, we need to travel parallel to the plane. Now, what are the vectors parallel to the plane? Well, we could have the vector AB and the vector AC. But we could have also had, right, the vector BC as well, right? We just require 2 vectors which are parallel to the surface of the plane and which are not parallel to each other, okay? So then, the key thing here is to understand that the equation is going to be R is equal to the vector OA plus lambda lots of AB plus mu lots of AC. In other words, we're not doing lambda lots of OB and lambda lots of OC, right? Because the vector OB is not parallel to the plane. It's the vector that goes from here to here. And the same thing is true with OC, okay? So that's what's going on there. So we need to find AB. So AB, let me just get rid of that, I think. So AB is going to be OB minus OA. So I'm just going to compute that quickly. So I will get 2 minus 2, which is 0, and then 4 minus 2, which is 2, and negative 1 minus 4 is negative 5. So that's the vector AB, and I also want the vector AC, and the vector AC is OC minus OA, so I'm going to get negative 3 minus 2, so that's negative 5. Okay, negative 3 minus 2 is negative 5, and 4 minus 4 is 0. So that's the vector AC. And so therefore, I can say that the vector equation of my plane is A, which was 2, 2, 4, 2, 2, 4, plus lambda lots of this vector here, 0 to negative 5, the vector AB, plus mu lots of this vector here, -5, -5, and 0. Okay, now then, we were not asked to find the vector equation of the plane, right? We were asked to find the Cartesian equation of the plane. Well, how do we find the Cartesian equation of the plane? We need to know the normal. So if we want to find the normal to the plane, how are we going to do that? Well, we take the cross product of these two vectors here, A, B, and AC, because those are the vectors which are parallel to the plane, right? So if I want to find the normal to the plane, right, I want to find the vector that's normal to the plane, then the cross product of A and C, of these two green vectors, A, B, and AC, is going to give me that, that vector. Okay, so I want to find the cross product of A, B, and AC. So let's do that. So n is equal to the cross product of 0 to -5 with -5, -5, 0. Now, there are a couple of different ways of doing the cross product, right? You could write it as the kind of IJK notation, like that, as the determinant of a 3x3 matrix. So that would be the first vector, 0, 2, -5, and -5, -5, 0, right? So you find the determinant of that. You could also use something called Sarris's law, which is a kind of an extension of this idea. But I'm hoping that you'll be able to compute this relatively quickly, and I think it's a good practice. So just watch me do it. So the first element, right, is going to be the determinant of these here, right? So if I want the first element, right, I ignore the first row, and I basically find the 2 by 2 determinant of this. So I get 2 times by 0, which is 0, minus -5 times -5. And -5 times -5 is positive 25, so I've got minus 25 there. Okay, and then what I'm going to do is I'm going to do the same thing for the second row. So the second row, I ignore that, and I'm finding the determinant of 0, -5, and -5, 0. Right, so write that out. 0, -5, -5, 0. So if I find the determinant of that, I got 0 minus positive 25. And of course, for the second element, it's negative. So I got minus 25, which is positive 25. And then lastly, I do the same thing for the third row. So I ignore these elements here, and I do the determinant of the top two rows. So 0 times -5 is 0, minus 10, right? So 0 minus 10 is plus 10. So I'm going to get that, okay? Now, for the normal, the only thing we actually care about is the direction. All right, so what we can do is we can actually scale this. Okay, so we can say, all right, I'm going to divide this through by 5, and I'm going to choose my normal vector instead to be -5, +5, and +2, right? So, because the only thing we care about is the direction, I've just divided through by the factor 5. Well, now, what did I say earlier? I said that we can get the Cartesian equation by doing r dot n is equal to a dot n. So I take r, which is the x, y, z vector, and I scalar product it with the -5, 5, 2. And I take my a vector, which is any position vector that's on the plane. So in this case, I'll use OA, which is 2, 2, 4. 2, 2, 4. And then I'm going to scalar product it again with the normal, which is -5, 5, and 2. And so if I expand all this, I'm going to get -5x plus 5y plus 2z is equal to -10 plus 10 plus 8. And of course, that whole thing there is just equal to 8. All right, so that would be the Cartesian equation of our plane. Now, having found this, one of the things we could do is we could also find the shortest distance to the plane. Okay, so why don't we do that? How can we find the shortest distance? Well, if you remember back, we can find the magnitude of the normal vector. So we're going to find the magnitude of, what was it, -5, 5, 2. So I'm going to get -5 squared is 25, plus +5 squared, which is 25, plus 2 squared, which is 4. So that's going to be the square root of 54. So if I was to take that number 8 and divide it by root 54, I'm going to get the shortest distance from the origin to the plane, right? So distance, or the perpendicular distance, origin to plane, will be equal to 8 divided by root 54. Now, I think it's a good opportunity to use Desmos to see what all of this looks like. So I'm just going to switch across to Desmos. Let me do that. Where was it? Okay, here. All right, so let's have a look at Desmos. Now, here what I've done is I've indicated the 3 points there, A, B, and C, onto the three-dimensional space. And now what I'm going to do is I'm going to put on the plane, right? So that's the plane, negative 5x plus 5y plus 2z is equal to 8. So hopefully you can see that this plane does indeed go through the 3 points. Okay, so let's look at part B of this question. The point D has a position vector 2i plus j plus 3k. Want to find the perpendicular distance from the point D to the plane A, B, C, right? So I've drawn the plane, drawn the origin, drawn a point D, which is floating in space. And what are we being asked to find? We're being asked to find the distance from D down onto the plane, right? So this angle here is going to be 90 degrees. And I'm going to call this point here on the plane, I'll call it E, so I give it a letter. Now, how can I find the distance from D to E? Well, again, what we're going to do is we're going to go from a trigonometric problem to a vector problem, right? So we want to draw a triangle first, and then we want to try to describe that triangle using either the scalar product or the cross product. Now, what do I mean? Let's say we've got another point here, A, right? We've already got 3 points that exist on the plane, A, B, and C. Let's just choose A as an example. And I'm going to form a right angle triangle with A, D, and E. So if I do that, I'm going to get a right angle triangle like that, that, and that. Okay? Now then, I'm going to also call the angle between AD and ED the angle theta. Now, if I do that, let's have a quick think. We can use trigonometry because we can say that the magnitude of the vector DE is going to be equal to the magnitude of AD times by the cosine of the angle between them, right? Because what we've got, right, this is the adjacent side, AD is the hypotenuse, right? So therefore the adjacent is equal to the hypotenuse times by the cosine of the angle between them. That should be fairly clear. Now, what was the trick that I applied at the very first introduction? This guy here looks very, very suspiciously similar to the scalar product rule, right? Because I know that A dot B is equal to the magnitude of A, the magnitude of B, times by the cosine of the angle between those two vectors. So I want a way where I can convert this into a scalar product, basically. Now, how could I do that? Well, the vector AD is that vector there. So let me just draw that on. That's the vector AD. And it makes an angle with this vector here, DE, right? And now DE is the normal vector to the plane. So actually that vector is the same thing as the normal, isn't it? Now then, if I was to fiddle with the equation I've got here, I can say I've got the magnitude of AD cos theta, and inside that, I'm going to sneak in the magnitude of the unit normal, right? Now, this is the trick that you basically do again and again and again. It's such an important trick for you to understand. I'm introducing this thing. Now, what does n hat represent? N hat represents the vector that's in the direction of the normal, but has got a magnitude of 1. Okay, that's what it means. What that means is that the magnitude of the unit vector is always 1. So basically what I'm doing here is I'm multiplying by 1. So this is actually the same as that. However, why have I done this? Well, because this now looks like this form here. So I can replace this entire expression, sorry, just let me scroll down, with the vector AD scalar producted with the unit normal vector. And the unit normal is the same thing as the normal vector divided by the magnitude of the normal vector, right? Because that's exactly what the unit vector means, right? I've got my vector, it's got like a magnitude of whatever, 7. So if I want to get the unit vector, I just take it and divide by 7, divide by the magnitude to get a vector of size 1. So what do I need to do in this case? Well, I need to find the vector AD. So the vector D is 2, 1, 3. Right, so I'm going to write that down. So O to D is equal to 2, 1, 3. And the vector OA is, I forget what it is. Let's just go back. OA was 2, 2, 4. Okay, so 2, 2, 4. And so therefore, the vector AD is equal to OD minus OA, right? So we've got 2 minus 2 is 0. 1 minus 2 is -1. And 3 minus 4 is -1. So I then want to do this scalar producted with the normal. So the distance that I'm looking for, the distance is equal to this vector 0, -1, -1, scalar producted with the normal, which if I remember rightly, let's just go back, was -5, 5, 2. Okay, so -5, 5, 2. And then we're going to divide that whole thing through by the magnitude of the normal, which was -5 squared plus +5 squared plus 2 squared. So let's do the scalar product. We get 0, -5, and then what's it? -2 over the square root of 54. And this is -7 over root 54. And you go, hang on, wait, how can the distance be negative? Well, essentially what's happened there is we got one vector that's like that. Let's say that's the vector AD. And the normal vector, which I'll do in green, is in this direction, right, like that, which means that the angle in between, so this guy here, is an obtuse angle, which is why we've got the negative. Okay, so all we've got to do is just got to turn it into a positive. So the actual distance is equal to 7 upon root 54. Okay, so that's going to be our answer. Now then, guys, I think it's essentially the really, really key trick that you need to get is this whole trick here, right? So I said earlier that what you're really doing is you're moving from a trigonometric problem to a vector problem, right? And if you can understand that, then I think you've basically cracked the FP1 vectors, okay? But it's understanding that step which is absolutely essential. Okay, so next we're asked to find the shortest distance between two lines. Now, I think really the key to understanding this is having a good visualization of what's actually going on. So in order to do that, I'm going to switch across to Desmos. And here what I've done is I've drawn the two lines in space. Now, what I want you to notice is that as I rotate these lines here, then the angle between them from our perspective seems to change, right? And what I want you to notice is that I can rotate them in such a way that actually those two lines appear to be parallel, right? So those lines appear to be parallel from one particular perspective. And this becomes even more obvious if I introduce the normal vector, or the vector that's normal to both the red and the blue line there. Because we can see there that the green line is perpendicular to the blue and perpendicular to the red. So from one perspective, those two lines, the red and the blue, are parallel. If you're still not convinced, what I'm going to do is I'm going to introduce two planes here, a red and a blue plane, right? So the red plane is a plane that contains that red line. The blue plane is the plane that contains the blue line. And both planes, right, are defined by the normal vector, that green vector there. Well, if that's the case, then it's pretty clear, I think now, that from this perspective, these two planes are going to be parallel, which means that there is a perspective from which the two lines are also parallel, right? So I think if you can see that, right, which is very, very hard to do on a 2D page or in a book, If you can see that and understand that concept, then these questions are going to become a lot more straightforward. Okay, so what I'm going to do is I'm going to shift back to the whiteboard now, and I'm going to try to draw out this idea. So what I'm saying is, imagine we've got this line here, or rather two lines, and in this perspective, the two lines are parallel. So I've got the line AB, let's say, and we've got the line here CD. Now, what we're asked to do in the question is we're asked to find the distance between these two lines. And by the way, actually, that's the same thing as finding the distance between the two planes that I just drew on Desmos, which will give you another way of approaching this problem if you think about it, and I'll do that a little bit later. But anyway, we'll just keep with this for the time being. Now, we know, furthermore, that there is a vector which is perpendicular to both of these. Right, so I'm going to draw that vector like that. So that is the normal vector. Now, how could I get the normal vector? Well, I would find the cross product of the direction of AB and the direction of CD, right? Because the cross product always gives me the vector that is perpendicular to both. Now, on the line AB, I know 2 points. I know, let's say, the point A. And on the line CD, I know 2 points. And let's say we just choose one, the point C. Now, what I can do with this is I can draw a right-angled triangle. So that's exactly what I'm going to do. I'm going to draw a right-angled triangle here. So we're going to draw a line going from A to C. And this line here will be in the same direction as the normal, like that. So what I end up with is a right-angled triangle where the hypotenuse is going to be the magnitude of the vector A to C, right? Can you see that? Because that's the vector A to C there. So I'll write that on AC. And the adjacent side is going to be the distance that we're looking for, which is D. And I can then say that we've got an angle between that hypotenuse side, between the vector AC, and also between this adjacent side. Now, this adjacent side is in the same direction as the normal vector, isn't it? So I can actually label that and say that this thing here is also in the direction of the normal. So how can I use this information? Well, I am going to start with a statement of trigonometry, right? Always what we're trying to do is we're trying to start with trigonometry and then fiddle it so that we end up with a vector problem. So how can I do that? Well, the cosine of theta will be equal to the adjacent side, which is D, divided by the hypotenuse side, which is the magnitude of AC, right? So if you're not sure about that, the cosine of that angle is equal to that side length there, which is D, divided by the magnitude of AC. And of course, what I can do is I can rewrite that and say that D is equal to the magnitude of AC times by the cosine of the angle theta. Now, wait a minute. This guy here looks a little bit similar to the scalar product, right? It looks quite similar to this thing. A dot B is equal to the magnitude of A times by the magnitude of B times by the cosine of the angle between the two vectors. Right, so we've got two vectors here. We've got AC and we've got N. We've got an angle between them. So we should be able to use this. Now, how can I manipulate this expression here so it looks like this? Well, what I can do is I can insert the unit normal vector. So that's what I'm going to do. So I'm going to get the magnitude of AC times by the cosine of theta. And then I'm going to multiply it by the unit normal vector there, or the magnitude of the unit normal to be precise. Now, how can I do that? The hat there means we've got a unit vector. What is a unit vector? It's a vector of size 1. So what's the magnitude of a unit vector? It's going to be 1, right? So this whole thing here in blue, that is just equal to 1. So what that means is that this side, this line here is equivalent to that line there. They're the same thing. So why have I done that? Well, because it means that this now looks exactly like that. So I can replace this line with the scalar product. I can say that this is the same thing as the vector AC scalar producted with the unit normal. So can you see what I've done, right? This is the key trick. This is the thing that you really, really need to understand, because it's happening with all these questions. We are starting with a trigonometric problem. We always want to start with trigonometry, and we are manipulating it so that in the end what we get is a vector problem, right? So we are moving from trigonometry to vectors. And the key way we do that is often with this unit normal vector here. Okay, that's what's going on. Okay, so now that we've got that, the problem should really become fairly simple. What do we need? We're going to need to find the vector AC. Well, that's going to be simple. It'll be OC minus OA. And we're going to need to find the normal vector. Well, how do I find the normal vector? I've got to find the vector that's perpendicular to AB and AC. And that means I've got to do the cross product of AB and CD, right? So I'm going to find the vector that's parallel to this line. That's the vector AB. So let me just do that over here. So AB will be OB minus OA. So 2 minus 2 is 0. 4 minus 2 is 2. Negative 1 minus 4 is negative 5. Do the same thing with CD. So CD is going to be equal to OD minus OC. So 2 minus 3 is 5. 1 minus 3 is 4. 4 minus... hang on, have I done that right? Yeah, 1 minus 3 is 4. 3 minus 4 is negative 1. Yeah? So I did OD minus OC. I just want to double check that again. Yeah, okay. And then the normal is going to be the cross product of those, right? So it's going to be the cross product of O2 negative 5 with 5, 4, negative 1. Now, I know there are a couple of ways of doing this, guys. You know, you could write it out as the determinant of a 3 by 3. You could use Sarris's rule and so on. I'm just going to get on and do it because at the moment, I'm not so much interested in teaching you how to do the cross product. I'm more interested in teaching about this, this method for the two lines. Okay, so my I component is going to be negative 2 minus 20, which is 18. Okay, so I'm doing it the fast way. And then the J component is going to be 0 minus 25, which is 25. But I've got to remember for J, it's negative. So that's negative 25 there. And then for the K's, I've got 0 minus 10. So that'd be negative 10. So that guy there, I believe, is my normal vector, which I'm just going to double check against the mark scheme, make sure that I am actually getting that correct. Yep, that's all okay so far. So we're doing good. And so then what I want to do is I want to find the vector AC and then take the scalar product of those two. So what's AC going to be? So I'll just move over here so I can see. Oh dear. The vector AC is going to be OC minus OA. So negative 3 minus 2 is negative 5. Negative 3 minus 2 is negative 5. And 4 minus 4 is 0. Okay. And so then I can say, all right, well, what was it that I wanted to find? I wanted to find AC dotted with the normal vector. Let me just get rid of that. So I want to find for the distance is equal to AC dotted with the unit normal vector. And what's the unit normal vector? It's the same thing as the normal vector, but divided through by the magnitude of the normal vector. Okay, so I'm going to do AC, which was 18, negative 25, negative 10. And I'm going to scalar product it with negative 5, 0. Right, so negative 5, 0. And I'm going to divide it all through by the magnitude of the normal, which is 18 squared plus negative 25 squared plus negative 10 squared, all square rooted. Okay, so now what I've got to do is I've got to put that into a calculator and see if it gives me the right answer. Okay, so I'm just going to put all that in. So 18 times by negative 5 will be negative 90. 25 times by 5 is 125. Now it'll be 0, won't it? So let's just do that. Okay, then I've got to do 18 squared plus 25 squared plus 10 squared. That gives me 1049. So it's the square root of 1049. Okay, and then that will be what, 35 over root 1049. And I'm just going to check that against the mark scheme, see if that's the right guy. Let me just check that out. Yep, that's correct. Okay, so so guys, I hope that was helpful. I'm going to look at it in another way in just a second, but the key thing I really want you to get is, firstly, understanding what we see on Desmos, right, that there's a perspective whereby the two lines are essentially parallel. And then what you can do is you can use that to create a right angle triangle between the two lines, or actually, if you prefer, between the two planes, really. And then you can write a statement of trigonometry, and with a little bit of manipulation using the unit normal, turn it into a vector problem. Okay, so what I would suggest you do, because you're further math students, right, is you do not memorize a formula like that. Right? It means you don't understand. Instead, try to understand all of those steps. Okay, so I said that there's another way to do this question, which is to use planes. So that's what we're going to do. So I'm just going to shift back to Desmos there. And so here I've drawn the two lines. And previously I put on these lines planes. And the planes include our two lines, right? So the red plane includes the red line. The blue plane includes the blue line. And what we can see is that these two planes are parallel to each other. And the reason is they share a common normal vector. Now, effectively, what this tells us is that finding the shortest distance between the two lines is the same thing as finding the shortest distance between the two planes, right? So if we want to find the perpendicular distance between the two lines, which is the shortest distance, it's the same as finding the perpendicular distance between the two planes. Well, how could we do that? Well, we find the distance of the red plane to the origin, and we find the distance of the blue plane to the origin, and then we take the difference of those two. Right now, we already know that because if you looked at the first part of my video, what I did is I showed you that if we've got the Cartesian equation of the plane, nxx plus nyy plus nzz is equal to some number d, then the coefficients of x, y, and z are the components of the normal vector, right? So these are the components of the normal vector to our plane. And then this thing here, right? Well, this is very closely related to the shortest distance from the origin to the plane. If we take this number and we divide it by the magnitude of the normal vector, then that will give us the shortest distance. Now, if you want the full explanation of why that is, then you go watch the first part of the video again. I'm not going to repeat, but that's the key idea. So effectively, what we've got is we have got two planes, right? We've got the plane which includes the line AB, and that has got the form 18x minus 25y minus 10z is equal to some number d. And also, the plane which includes the line CD has also got the same form, right? Because the normal vector is 18, negative 25, negative 10. So they're going to share these same coefficients. Now, what all we need to do is to find out what this value d is. How can we find out what that value d is? Well, we just substitute in a point that we know is on the plane. Well, if we've got the line AB on our plane, then we know that either this point here is on the plane or that point there. So we can just substitute these points in. So that's what I'm going to do. I'll substitute in the point A. So I've got 18 times 2, which is 36, minus 25 times 2, which is minus 50, minus 10 times by 4, which is minus 40. And that's going to give me there d. Okay, so if I add up all of that, what I get is I get negative 54. So in this case, d is equal to negative 54. And so I can say that this particular plane, which includes AB, is 18x minus 25y minus 10z is equal to negative 54. And I'm going to do the same thing for CD. So CD is going to equal to 18x minus 25y minus 10z. I'll use a different letter, right? So call this k, doesn't really matter. And I'm going to substitute in a point. Well, let's substitute in the point D, which is 213. So if I do that, what I'm going to get is 18 times by 2, which is 36, minus 25 times 1, which is negative 25, minus, what was the other point? 3, minus 30. So k is going to equal to 36 minus 25 minus 30, and I get that's negative 19. So k is equal to negative 19. Well, okay then. We can then find the shortest distance, can't we? So we're going to take both of these and we're going to divide them by the magnitude of the normal vector. So the magnitude of the normal vector is going to be equal to the square root of 18 squared plus negative 25 squared plus negative 10 all squared. Now if I just do that, 18 squared plus 25 squared plus 10 squared equals square root answer. Okay. So that was the square root of 1049. Okay, like that. And so what I say, okay, well, the shortest distance of this plane to the origin is going to be that negative 54 over the square root of 1049. And what's this one going to be? It's going to be negative 19 divided by square root 1049. So negative 19 over square root 1049. Well, what's the difference between these two? Well, what's the difference between negative 54 and 19? Okay, it's 35, right? So the difference between those two is equal to 35 over square root 1049, right? Which is the same thing as the answer we got in the previous part, right? So if we really understand what's going on here, if we're nice and confident, and usually if we've got a good visualization and we can think about these problems in many different ways, then hopefully this is not going to be too difficult, or at least even when it is difficult, it is manageable. Okay. Now, if you're finding this video helpful, if you found it useful, please like, subscribe, share it with your friends. I hope to help more people who are studying further math.